Hey everyone, and welcome to this explainer. Today we're going to completely demystify the fascinating physics of light. I mean, we rely on light to see absolutely everything around us, right? From the reflection in your bathroom mirror to the majestic colors of a rainbow. But how exactly does it behave when it hits a curved surface? Well, we are going to trace the incredibly clear, structured journey of a single light ray to find out exactly how it all works.
Okay, let's just dive right into our logical roadmap for today. We'll be covering 1. The basics of light, 2. Meeting the spherical mirrors, 3. Tracing the light rays, 4. Mirrors in real life, 5. The math of magnification, and finally, 6. The illusion of refraction. And hey, don't worry if math isn't your favorite subject, we're going to make this complex topic incredibly approachable.
Section 1. The basics of light. Before we start bending and bouncing light all over the place, we really have to establish exactly how it moves through the world.
Now, light can behave in some incredibly complex ways. Sometimes it acts like a wave, and sometimes like a particle. But for our purposes, we just need to look at a sharp shadow cast by a solid object. That simple, everyday thing confidently proves that light travels in straight, predictable lines. We call this straight-line path a ray of light, and honestly, it is the foundational rule for absolutely everything we are about to explore today.
Section 2. Meet the spherical mirrors. Now that we've got our light ray traveling in a straight line, let's go ahead and introduce the main characters of our story.
So, spherical mirrors are exactly what they sound like. They are mirrors whose reflecting surfaces basically form a part of a hollow sphere. To easily anchor this abstract geometry to reality, just imagine going to your kitchen and looking at your reflection in a shiny spoon. The inner surface, which is curved inwards, kind of like a cave, acts as a concave mirror. But if you flip it around, that bulging back surface is your convex mirror. It's that simple.
To really understand how these mirrors manipulate our light ray, we need to rapidly build a map of a mirror's anatomy. We'll start with the pole, represented by the letter P. Think of this as our central anchor point. It sits exactly in the dead center of the reflecting surface of the mirror itself.
Next up is the center of curvature, or just C. Remember how we said these mirrors are parts of a sphere? Well, C is the literal center of that imaginary sphere. It sits completely outside the reflecting surface, representing the very heart of the invisible globe our mirror was cut from. And the distance from the pole to the center of curvature? That's simply the radius of that sphere. Finally, we have the principal focus, which we denote with an F. This is an incredibly important spot, and it sits exactly halfway between the pole and the center of curvature. The distance from the pole to this specific focus point is what we call the focal length. And this perfectly illustrates the core difference between our two types of mirrors. Just look at how they handle incoming light rays that run parallel to the center axis. Concave mirrors converge those parallel light rays to a real, physical focus point right in front of the mirror. Fun fact, if you hold a concave mirror to the sun and focus those rays onto a piece of paper, the concentrated heat will actually ignite it. Convex mirrors, on the other hand, spread the light out. The rays are reflected outwards, making them appear to diverge from an apparent, virtual focus point hidden behind the mirror.
All right, Section 3. Tracing the light rays. With our terminology totally locked in, we are finally ready to learn the actual rules of the game.
Think of this as your complete cheat sheet. By following just these 4 simple, step-by-step geometric rules, tracing light rays transforms from a daunting, complicated task into a totally solvable puzzle. For instance, any ray coming in parallel bounces right through the focus. Any ray passing through the center of curvature bounces straight back along its exact same path. It's just simple, elegant geometry, perfectly following the basic laws of reflection.
So, how does all this build visually? Well, if we take an object, let's say an arrow, we don't actually need to trace every single light ray bouncing off of it. By intersecting just 2 of those rule-bound rays originating from the top of our object, we can pinpoint exactly where and how an image will form. The exact spot where those 2 reflected rays cross, that's exactly where your image appears.
By mapping out these ray diagrams for different object distances and synthesizing the data, you can start to see a really clear narrative unfolding. As an object moves from infinitely far away, getting closer and closer to a concave mirror, the resulting image drastically shifts. It starts out as this real, inverted, and tiny little point. But if you bring the object close enough, specifically between the pole and the focus, suddenly the image snaps into a virtual, upright, and highly magnified reflection located behind the mirror.
Section 4. Mirrors in real life. Okay, so all of this geometry is great on paper, but why does any of this ray tracing actually matter to you in your everyday life? The truth is, we utilize these specific light-bending properties constantly. Remember how we just saw that concave mirrors magnify things when they get super close? That is exactly why dentists use them to zoom in on a magnified upright image of your teeth. And it's why people use them as shaving mirrors. Now, what about cars? Vehicles use convex mirrors for their side rearview mirrors. Because convex mirrors always produce an erect image and their outward bulge provides a massively widened field of view, they allow drivers to safely see a much larger area of traffic behind them.
Section 5. The Math of Magnification. To truly master these tools, whether we're designing a high-tech dentist tool or a simple car mirror, we do need to ground our visual rules in the precise reality of mathematics. But please, don't let the math intimidate you. Instead of thinking about abstract geometry, just think of this new Cartesian sign convention as a standard XY coordinate graph where the mirror's pole is the 0, 0 origin point. Anything measured to the left of the mirror is negative. Anything to the right is positive. Pointing up is positive and pointing down is negative. It's just a universal grid designed to keep all our math perfectly organized.
So here is the crucial takeaway. This singular equation known as the mirror formula universally links the object distance, the image distance, and the focal length for literally every single spherical mirror scenario. By just plugging in our positive and negative numbers from that Cartesian grid, we can calculate exactly where an image will appear, and we don't have to draw a single ray diagram to do it.
And coupling that mirror formula with this super straightforward magnification ratio allows us to calculate exactly how enlarged or diminished an image will be. Magnification is really just the height of the image divided by the height of the object. What's wonderfully elegant here is the built-in logic. A negative sign in your final magnification number handily tells you the image is inverted and real, while a positive sign tells you it's upright and virtual.
Section 6. The Illusion of Refraction. So far, we've successfully decoded the physics of light bouncing off surfaces. We've mapped its path, explored curved mirrors, and even learned the math. But light has one more major trick up its sleeve.
Everything we just discussed relies entirely on light reflecting back into the same medium it came from. But to leave you with a provocative thought, consider what happens when light actually enters a new transparent medium, like water or glass. Have you ever noticed that a pencil sitting in a glass of water appears to be disjointed or completely broken right at the surface line? Why does light totally change its direction when it crosses that invisible boundary? Well, that specific phenomenon sets the stage perfectly for our next explainer, where we'll dive deep into the illusion of refraction. Until then, keep questioning everything you see.